Alright, so today myself and Simone will going to talk about AUTOSAR application development for the SDV era. So let's get started. So what is software-defined vehicle? It's very complicated to write the definition for it. So for the heck of knowing it, I googled it. It came with several definitions. Everyone has their own way of saying what is SDV. So I took a different stab at it. Instead of defining SDV, what is the impact of SDV on the automotive community? Actually, it is bringing the entire community together, including OEMs, suppliers, service providers, tool vendors, IC vendors, and also cloud service vendors have come together to prepare a production-ready SDV. And also, as you can see there, everyone is joining hands together. For example, Elektrobit and us and other tool vendors have come together here today to show how AUTOSAR adaptive development can be done in the SDV era. And by that, it is bringing a greater impact in the automotive world to ensure and encourage driver safety, security, and providing a catchy experience. All right. Now let's fasten our belts. Simone will going to take us back to the past before driving back to the future.
Okay, thank you. Yes, back to the past. What does that mean? Maybe that's still the present, actually, not just the past. So you can imagine a typical automotive project. Like this one, we have several suppliers, and the collaboration happens throughout using specifications, maybe software components distributed by some OEM. And in this case, this is an example from one of the projects I worked in the recent years. So we had secure service-oriented communication. That meant the communication what should be secured against attackers, so there was an authorization added and also some authentication to the SDV messages to protect them against tampering. What happened? It was distributed, each supplier worked on it independently, did some testing, and then after some months, there was the first integration test done at the OEM. So that meant every supplier packed the ECU into a suitcase, traveled to the OEM, and then they did an integration workshop. The problem was that on first trial, nothing worked. And this is typically the case because, of course, specifications aren't perfect. The software components aren't perfect if it's a new technology. And that means there has to be something that goes wrong in the first trial. The problem is you lose a lot of time by that. And you can see this pretty well on this V cycle, so that you start on the left-hand side with specifications and then go down and implement it. And on the right-hand side, in the parallel, you start preparing the testing part of it, the right-hand side of the V model, as we call it. But that always implies some delays. And in the SDV era, we all know, and we can increasingly see that this is too slow. And how can you improve that? One thing is adding something before, at an earlier stage, before we test it on hardware. And this is software in the loop testing is a good example for that. And this is actually what we have also, we will also show as part of this presentation, a use case for a software in the loop verification, helping to accelerate software development. And by that, we can virtualize system tests. So we can, instead of having to wait for assembling a hill, we can do that all in software. And we gain another benefit by having a scalable software-defined test bench. And every developer worldwide can basically access it. The other component that can help here to speed it up is model-based development, like MATLAB Simulate. And you can even generate embedded code out of that and test it. So you can have a really closed-loop, continuous verification kind of working along the model. What does virtually use mean? There's a lot of misunderstandings in that terminology. So I'm briefly going to introduce that. If you have detailed questions later on, come to me. I can give you more details. But really roughly, there's the levels ranging from 0 to 5. Starting from 0, you have the lowest level, which is model-in-the-loop testing. You basically have an algorithm model in a tool like MATLAB. You run that, and that's already a virtual ECU on a very low level. It's not production code, but it's still already useful. If you want to test the real production code, then you would use level 1. And as you can see on the top of this slide, there's post-compiled mentioned. Post-compiled means you take the production code, maybe it's in C, it's generated from the model, and you compile it for your PC. So you're not for the target platform, but for the PC. That gives you the opportunity to run that code natively in an efficient way. If you need some more complexity, and if you want to also test the interaction with the basic software, then you use level 2. And if you want to use the real basic software, then you use level 3. Right, at level 3, you have, for example, the diagnostic module, like you would have it in the real ECU, same configuration, and NVM and all the other hardware-independent modules are exactly identically configured, except for these layers like the ML, which you, of course, cannot directly compile for the PC. So those you replace by simulation equivalence. And then level 4 is yet another completely different technology. Here you can run the same binary as on the target ECU, but that requires a hardware simulator. So today we're going to focus on level 4. Okay, let's get back into the future.
Right, it's kind of future and also present for a few people. So, as Simon mentioned, there are several challenges you might encounter while developing the SDV software, like how do we address that? We touched upon testing and validation. I'm extending a bit more here, how you can develop faster without compromising on the software quality goals. So that's by following the adapting DevOps workflows and best practices. So that will come with reliable operation cycles and extending that to virtualization, as Simone mentioned, and also automate and scale your application on the cloud. So with NPD, you can develop DevOps recommended practices, and then you Simulink applications, and also you can develop your software applications in Simulink, where you can do the model-in-the-loop verification, software-in-the-loop verification, also process in the virtual verification as well. So Simone mentioned about virtual ECU level simulation. So with AUTOSAR classic applications, if you have a requirement to simulate your application software which are interacting with the basic software services like NVM and diagnostics, you can still do that in Simulink. That will essentially help you to achieve level 2 virtual ECU simulation. And then Simulink and MATLAB applications can be deployed on the cloud as well. So with this model-based design, Simulink definitely helps the automotive companies to achieve safety goals as well. That's essentially by shifting left. So let's dive into how do we shift left by virtualization. So there are a few ways. I'll just highlight them today with examples. The first one is with creating a virtual vehicle. That's by developing software components, driving scenarios, user commands to simulate the overall performance of your application. As you can see there, I have an vehicle control unit application implemented in Simulink, and I'm doing the simulation. Here you can visualize and analyze how your output is acting as per your input, and you can confirm whether it is acting as per your requirements as well. The next way is prototyping. So you can develop your applications and deploy it in the host-based environment before you even tackling on the real hardware. So here, what I'm trying to do is I'm trying to deploy an application developed in Simulink and deploy it on the Linux computers via the OTA server. So I have an example here. I have 3 adaptive AUTOSAR services developed in Simulink at the architecture level and with the behavior algorithm in it. So I want to deploy it on the 2 Linux computers via this Orbit Eclipse server. It's a free OTA server. So I will update that in the OTA server, and that will be deployed on this Linux computer. Even at that level, what you can do is you can monitor and tune the signals, and you can visualize how your application is acting based on your inputs. Subsequently, I will add one more adaptive service component. So I have 4 services here. So for that, I will again update on the OTA server, and I'll ask them to roll it out on the Linux computer. So in this way, you can prototype as well as deploy it on the Linux target via the OTA server. So yeah, now let me talk about the 4th way of virtualization. That's by creating virtual ECUs of production-ready AUTOSAR classic and adaptive virtual processor models. So I have a vehicle control unit which is following the adaptive platform, and the battery management system following the classic platform. So those applications are developed in Simulink and integrated with the ED stack and running on the POSIX OS as well as vRTOS, and finally deployed on AWS. So now Simon will going to talk about how did we really achieve this virtual ECU for both classic and adaptive platform, and he'll talk about the challenges and what is the solution is done for this workflow.
Yes, the challenge was of course that we have developed applications in a model. We want to integrate that in different environments. Different environments means depending on functionality, we want to have it on the classic AUTOSAR ECU or on an adaptive AUTOSAR ECU. And we want to verify that that what we have already done in the model behaves the same way in the virtual ECU with the real middleware. And there can be differences, as you can imagine. For example, there could be a misconfiguration in the sub-IP stack leading to signals not being processed as intended. So you want to verify both worlds, right? It's not sufficient to just to just verify the model. You also want to verify the complete integration. So, and that's what we wanted to achieve. So basically, the solution we choose is we customize the application code for specific middleware. That's basically what we get as a result from the code generation. And then we integrated that with real middleware and deployed that within virtual ECUs. So what you can see on the bottom is basically all the components that we have used as a heterogeneous simulation environment. And for the classic AUTOSAR, we used a level 3 virtual ECU based simulated in Synopsys Silver. For the model in the loop test, we used the Simulink. It has an included verification feature. And for classic, for adaptive AUTOSAR, we have been using a bare metal Linux integrated with adaptive AUTOSAR, and then that has been executed as a separate entity. So by that, our demo use case that we have also that we're also showing on our demo booth, by the way, is a kind of simplified powertrain application. So you have a combination of an in-vehicle infotainment where you can switch between different driving modes. Then you have a vehicle control unit, which is a kind of central coordinator. And on the other hand, you have the battery management, which is modeled to keep the battery temperature under control and so on. And what we basically do is the battery management is a typical real-time classic AUTOSAR safety-related application. So we integrate that on a classic AUTOSAR ECU. The vehicle control unit goes to an adaptive AUTOSAR ECU, and the IVI is an Android application. And we attach to that test framework to stimulate that and to get the results. And of course, it's also needed that we connect them, right? So we have a virtual network, we stimulate that from outside, we run that, and then we can basically get a test result and even scale this up because we run it in the cloud. That's the general idea.
As Simon mentioned, we have our demo being displayed out in the demo showcase. All right, so here you can see that it's very tiny, but you can switch the mode of the simulation. So I'm switching that to sports mode, and you can see on the graph the discharge current drop drastically. You can see the data being changed in the both classic as well as the adaptive ECU. That's the vehicle control unit as well as the battery management system. So I would encourage you to check it out, and if you have any more questions, stop by and ask us in details if you want to. And with that, we would like to conclude this talk with 2 key takeaways.
Okay, so okay, yes. SDV need cross-domain testing environments built from a diverse set of tools, right? So you need to combine Elektrobit, for example, or other tools with other testing environments and test frameworks. The virtualization of ECUs enables early verifications and scalable test executions so you get faster using it. And as it briefly showed up in the virtualization level slide, there is no real correct virtualization level. It's a trade-off. It depends on the use case, and whatever it fits your use case is correct.
Right. Then we need to shift left. So that it requires a mindset change to create a production-ready SDV. And that comes with, we talked about shift left via different types of virtualization, right from creating virtual vehicle, prototyping, and virtual ECUs. So that will enable you to validate and reuse your software and do the integrations as intuitively as possible. So that accelerates the development. But we have a bigger goal. We need to create a software factory, and we want to do the SOP, and we want to close the loop with the 5G or cloud. And then push the update even after the SOP to increase the performance, which is the goal of software-defined vehicle. Thank you.
Thank you for your presentation. Especially I would like to thank Simon for his presentation since he arrived this morning at 6 o'clock. So he's still a little bit tired after the flight, but he managed it extremely well. Okay, thank you. Are there any questions to both speakers? Yeah, I see.
on the simulative part, so I would ask my question more on the modeling part. As you have created a heterogeneous system about AUTOSAR Classic, AUTOSAR Adaptive, and you use obviously service-oriented computation. So how did you model the services? Was that done on a more abstract level, on a system level, or was it always, let's say, more or less a kind of copy and paste in every model which would be deployed either in Classic or Adaptive?
Yeah, so we use some IP for the communication aspects. And with Simulink, there is some IP binding support where it will provide the some IP implementation calls to it that will enable you to communicate. So we kind of do the configuration in the Simulink work, but it will be taken care at the code gen level, and then it will look for some IP implementation from the ED stack. So that's how we.
Yeah, but at least for a classic component and an adaptive component, you have two models. Talking more or less about providing a service and consuming the service. Is there a kind of abstract model possibility meanwhile, for example, in System Composer for your company?
That's a great question. It's not there yet.
Okay.
But I like your aspiration. Yes, we'll let's talk more on that.
Thank you.
Yeah.
So there was another question, I saw it somewhere here. You wanted to ask? No more questions? Okay, thank you, Svetlana. Thank you, Simon.